So today we want to talk about triple integrals and cylindrical and spherical coordinates. So I want to continue talking about this. Remember that we have the three ways that we can describe solids in R3. We have rectangular coordinates where we have dz, dx, dz, dy, and dx. In cylindrical coordinates, we have r, theta, and z. Since one of those d theta is a measure of an angle, not a length, we need the arc length to turn it into a length. And that's why we have the r. That r turns d theta into a length. Specifically arc length, but that's what the r is there for. It's to make d theta into a length so that r dr d theta dz is a volume, length times width times height. Just like dx, dy, dz. In spherical coordinates, two of the coordinates are angles. So we needed two factors to turn d theta and d phi into lengths. Rho turns d phi into a length, and rho sine phi turns d theta into a length. So the rho turns d phi into a length, and rho sine phi turns d theta into length. This is all based on the arc length, where we multiply the angle by the radius. Just like when we find the circumference of a circle. The circumference of a circle is 2 pi. It's the whole circle multiplied by r, the radius. Circumference is just arc length, but it goes all the way around. Pi times the radius will give us the semicircle. Pi over 2 times the radius will give us a quarter circle, and so on. So it's just proportion. And we drew a few pictures showing that the change in angle, we need the lengths we need to change our change in angle into a length. So what we want to do now is take some shapes that we worked with in the past and write triple integrals for them in cylindrical and spherical coordinates, if at all possible. So recall. In the past, we had looked at a circular paraboloid bounded below by z equals x squared plus y squared, and above by z equals 9. We had written a definite integral we had written a triple integral for this solid in the past. We integrate the x's in rectangular coordinates. We would integrate the x from -3 to 3. We would integrate the y from the negative square root of 9 minus x squared to the positive square root of 9 minus x squared. And we'd integrate z from the paraboloid up to the top plane, which is a 9. And here we integrated dz, dy, dx. And we had calculated the volume by integrating the function 1. The integral over w of 1 dv will tell us the volume of the solid w. At each point in the solid, we're assigning the value of 1, and then dv is a volume. Then we integrated this, and we ended up with one very strange integral when we got down to the dx integral. And it didn't match how we would find the volume of this solid using a dx integral. Or it didn't correspond to thinking of this solid as a solid of revolution. It's because we ended with the x, and the cross section perpendicular to the x-axis is a bunch of parabolas, with the big parabola in the middle, and then the parabolas going up the sides of our circular parabola. So that's why that expression looks so strange, which is why we wanted to calculate it from another angle. What we wanted was multiple ways to arrive at the same volume of the solid. What we want to do today is recalculate the volume, but instead start by writing an integral, a triple integral, in cylindrical coordinates. So I want to write a triple integral . I'm just going to call this the solid W. So what we want to do is write a triple integral for the volume of the solid W in cylindrical coordinates. And then we want to do the same thing for spherical coordinates. So take a few minutes and start with cylindrical coordinates. You have a few options for how you're going to do the cylindrical coordinates. You can choose whatever order you want, dr, d theta, dz, or whatever order you want, dz, d theta, dr. But what we're going to have to do is include the r in our dv. So in cylindrical coordinates, we're going to want to write a triple integral. We're going to integrate the function 1 to get a volume, but included in the dv is the factor r. So we have a few decisions to make. what is going to be, what's the easiest choice for our constants? What should we open with? What's our first integral? And then that'll tell us what the middle one should be. Let's think about this. It sometimes helps to look from the top down. And when we look from the top down at this solid, we see a circle with a radius of 3 centered at the origin. So the top down view has a circle. Okay, we'll just pretend that this is a circle. So this circle, which we described before, has x squared plus y squared equals 3 squared. But we want to start thinking in terms of cylindrical coordinates. Here's one thing that we can note. We want to go all the way around the circle. We want to start off theta equals 0 to theta equals 2 pi. So here's where theta equals 0 and where theta is equal to 2 pi. So an easy choice to make would just be to use that as our constant. Remember, the last integral has to be constants. So maybe we can put theta at the end and just integrate from 0 to 2 pi. Let's go to the first parts. So we're going to integrate all the way around from 0 to 2 pi. We also got to describe what z is between. And z still goes from the paraboloid x squared plus y squared up to the z equals 9. Z equals 9 is in cylindrical coordinates, no problem, but z equals x squared plus y squared is not. So if I want to integrate z, we know it stops at 9, but I can't write x squared plus y squared. That's in rectangular coordinates. So fortunately for our heroes, we can translate our, and this is why I picked the circular thing, because lazy teacher, kind of lazy. We picked a circular thing because it's easy to translate x squared plus y squared into polar coordinates, or in this case, cylindrical coordinates. What we know is that r is the square root of x squared plus y squared. So x squared plus y squared is equal to r squared. So to convert, this is the z in rectangular coordinates, but if you want the z in polar coordinates, x squared plus y squared is equal to r squared. This is still x squared plus y squared on the bottom, up to 9 on the top, but we're going to have to retranslate our circle x squared plus y squared into polar coordinates. So we'll go from r squared up to 9. Any questions? I wanted to write x squared plus y squared as my starting z, but that's in rectangular coordinates. I replace x squared plus y squared with r squared to get the cylindrical coordinates. The last thing we need to do is figure out what values of R are going to be in play. And since I want all the parts of the solid from the center all the way out, R is going to start off at 0 and go out to a maximum of 3. If we look at this from the side, I'll take advantage of the symmetry. If we look at this from the side, I tried to change my Y into a Z. It became one of those true false F's, T combination F's that you try to put when you're doing a quiz and you're not sure if it's true or false. So you put true or false. You know what I'm talking about? And you're like, oh, well, I'm not sure. Oh, that's a T actually. But the statement was false. Oh, no. See, it has the thing, it's an F. Oh, but it was actually true. That middle mark, that's just a stray mark. It's just kind of a, maybe you should hand out cleaner papers, teacher. When you're back in the corner, you have to go on the offensive. You shouldn't hand out such messy papers. True or false. What are we talking about? Oh, yes. So if we look at what we're integrating to, we're integrating z equals r squared up to 9. This parabola is z equals x squared plus y squared. Oops. Sorry. This parabola, if I pick a point on the xy plane, it's at a distance of r from the origin. And since we're making a parabola, that means z is equal to r squared. So looking at it from the side, we can see we want to integrate the bottom, z equals r squared, the parabola that we're looking at, up to the top at z equals 9. Here is the piece that we're going for. The bottom is at r squared on that parabola. And the top is at 9. So we'll integrate r from 0 to 3. We'll integrate theta from 0 to 2 pi. And we'll integrate z from r squared to 9. Bottom to top, inside out, beginning of the circle, end of the circle. Any questions? Is everybody okay? So what we need to do now is actually calculate the integral, make sure that we get the same value that we had before. If we get a different value, then one of them has to be wrong, or both. both being wrong satisfies the condition, one is wrong. So let's integrate this. I didn't give myself enough space. So we're going to integrate from 0 to 2 pi. The integral from 0 to 3. The integral from r squared to 9 of 1 r dz dr d theta. The big idea here is we want to make sure that that r is part of the stuff that we're integrating, even though it showed up in this triple integral to be part of the dv, to turn the d theta into a length. It's still part of the function that we're integrating. So when we integrate this, the first thing we get is r times z, because we're integrating with respect to z. So we'll have the integral still from 0 to 2 pi, still from 0 to 3, rz evaluated from r squared to 9. Now we're plugging in z equals 9 and z equals r squared. So we'll have 9r minus 9r squared dr d theta. Any questions? Now we integrate dr, and we have this function of r, so we're going to have to actually integrate. Sounds like work. Not a fan, so we'll have 9/2 r squared minus 9/3 r cubed evaluated from 0 to 3. And now this is starting to give us some hope that this is going to work out to our, I think it was 40.5 pi. So let's evaluate. We only have to plug in the 3 because there's no constant here. So we'll have the integral from 0 to 2 pi of 3 squared is 9 times 9 is 81 over 2. Minus 3 cubed is 27 times 3 is 81. And so the 81/2 minus 81 is a negative 81 over 2. Now I'm wondering where I dropped the sign somewhere. Nine R. This one? Oh. Aha. But not 9, right? Just R cubed. So 9r squared, and this is going to be a fourth, r to the fourth. Oh, that works. All right, nice catch. 10 points for you, minus 100 for everybody else. I'm just kidding. It was a team effort. Negative 100 for everybody. A sacrifice. We should do that. We should have tests by champion. The class should be able to elect a champion to take the test. I want to talk about, so you'd have to collaborate to find out who among you has the greatest skill, right? Because you only get to pick one. So I'm like, all right, everybody has to take this test. The class is like, oh no. We elect, and then you pick your student third. We elect Sir Braun to stand for us. He is our champion. And then that one person takes a test. And you all have to watch, but you don't have any input. So like put the champion in the room with the test. And you put a camera and you watch, just like watch them do the work. That way, when they make a mistake, the whole class will be like, oh no. And then when they fix it, they're like, oh yeah. And you're like cheering on. Then they would turn in the test. And then if you all approve of their work on the test, I'll be standing there like this. And if you approve of their work, then you start cheering. I'm like, oh, no. And then everybody gets whatever grade it was. Thumbs up, and everybody gets an A. And then you'll be like, oh, but dude, what if there's a student that actually can't do any of this work? And they're benefiting from this other person's decisions and expertise. I would kind of suggest that that's like the point of like civilization. You're supposed to benefit from other people's expertise. That's why we get together and share knowledge. But then you're like, oh, but America and competition. I'm just coming in here trying to ruin everything about higher education as it stands. I don't like the money aspect. I don't like the competitive aspect. I'm against both of those things. And yet, what are the biggest things that we're worried about in education? Money and competition. You know what I mean? Then people start looking at this game and saying, hey, this game is rigged. And then all of a sudden, it just turns into improv. And then the people that run the school are like, oh, yes, and the students be like, oh, you're going to be doing something about that? How about this? Best I can do, we're going to say that we care about the problem and then not actually do anything to address it. How's that? How's that? But we'll say that we care. Does that work? And then when people are like, oh, fuck no, that's not going to work. They go, hang on a second. The standard play isn't working. You know what I mean? At least now I'm getting the 40 and a half that I expected. Thank you for that. I don't always pay attention when I'm doing my work. So this gives us the integral from 0 to 2 pi of 81 over 2 d theta. So that's going to be 81 over 2 theta, evaluated from 0 to 2 pi. And that will give us the 81. Now I'm off by a factor of 2. Oh, over 4. Yeah, that's 2. Heck. Questions? If we compare this, excuse me, if we compare this triple integral to the triple integral that we had before, where we had bottom to top, left to right, up, front to back. For the most part, in cylindrical coordinates, we got 0 to 2 pi and 0 to 3. Two of them are just constants. If I replace the r squared with 0, I'm going to get the volume of the cylinder with a radius 3 and a height of 9. Because when we just have constants in our triple integral in cylindrical coordinates, then we're looking at a cylinder. Just like if we had built a solid that was a rectangle in rectangular coordinates, then the x, the y, and the z will all be constants from -3 to 3, from left to right, and then from bottom to top. So if we just do constants all the way around in rectangular coordinates, that gives us a rectangle. In cylindrical coordinates, that gives us a cylinder. And in spherical coordinates, it's going to give us a sphere. If we just make constants all the way around. Notice that if we wanted to carve this circular paraboloid out of a rectangle, from -3 to 3, that would just be from left to right, or sorry, from back to front. But if we go from left to right, we've got to chip away that rectangular part by saying 9 just doesn't go between -3 and 3. 9 goes between these two circles. If we have a cylinder, oh, right here, from 0 to 2 pi, that's giving us all the way around. And then from the 0 to 3, that gives us a cylinder of radius 3. What we're chipping away is the z from r squared up to 9. We're chipping away the bottom. Instead of making the bottom equal to 0 and having a flat bottom, we make the bottom equal to r squared. And so we can think of chipping away at a cylinder to make our circular parabola. Any questions? In rectangular coordinates, we had to chip a rectangle or the circle out of the rectangle. And that's why the dy goes from the negative square root to the positive square root. Didn't have to worry about those two in the cylindrical coordinates. 0 to 2 pi goes all the way around. 0 to 3 in r gives us that full cylinder. We have to chip away the bottom. We have to chip twice in rectangular coordinates. How's everybody okay? We need to be thinking about that when we go to write a triple integral for w in spherical coordinates. What kind of a mess are we going to get ourselves into? The one that I want to point out is the fact that the top is flat. Spherical coordinates are good at building things out of spheres. Carving this solid out of a sphere is going to be a little difficult. How are we going to get the top where z is equal to 9? How are we going to make that flat? I can't just set rho equal to 9, because if rho is equal to 9, as soon as p starts moving off, we get this rounded top. We wanted a spherical top. Then spherical coordinates are going to be awesome. We don't want a spherical top. Spherical coordinates are going to be a problem. And the reason I'm warning you of this is because rather than doing spherical coordinates, the most difficult one today, I'm going to leave it as a problem. This is the question that I'm not going to be answering today. How do I write this in spherical coordinates? Think about what constants for all. If I just have constants in my spherical coordinates, what's that shape going to be? And then think about how you're going to carve out this shape from those spherical coordinates. Good question. If I wasn't so predictable, I would kind of imply that I'm about to show you the spherical coordinates for this particular solid. And I'd add to it by saying things like, once we do this, then triple integrals in all three coordinate systems will become crystal clear forever. And you won't even have to work at it. It will just be effortless. But as long as I do it right now, Only if I write this integral right now will anything ever make sense in Calc 3 again. I can make it super easy just by right now showing you the spherical coordinates for this particular solid. So let's do that and solve all the mysteries of Calc 3 and then say, oh, we're out of time. So that's your Blu-ray bonus material question. I want spherical coordinates for this circular paraboloid. It's going to be super messy and annoying. I'll take your suggestions tomorrow. Anybody who doesn't come up with the proper coordinates, one of you will be voted off the island. Wait, no, I'm mixing up my shows. That doesn't happen. We can't have voting off the island in a math class because I would be the first one voted out. It's like, when we voted, these should go. And our champion will be grading us from now on. All right, that's it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.